Right. Which is a novel generalization of algebraic theories that I'm working on with the purpose of being able to write your boilerplate informalizations for languages where there's more going on in context than just abstraction, and this is work in progress. So to clarify what I mean with boilerplate, so in your language, some things that you may want are admissibility of renaming and substitution, soundness, canonicity, normalization, decidability of equality, maybe an interpreter or compilers, including deshiggerings, and a pretty printer. And every time you try to formalize or implement one of these things, you will face boilerplate. And to make this a bit more concrete, let's look at the Menkar proof assistant that I've been working on for a year and that had the intention of implementing multimodal and pre-sheaf type theory. And what you see on the left are a bunch of program components. They're more or less similar to the list that I just gave. And above you see all the syntax constructors of the language, and mind the 3 dots, there are many, many more than just these few. And so each of these program components needs to traverse the syntax, and so it needs a case for every syntax constructor here. So every little box in this table needs to be filled. So every box is a piece of code. All these pieces of code are very similar and they're all different, so you need to write them all, and then if you make a change, you need to change them all, and this is a disaster to maintain. Fortunately, I've been able to make a few optimizations, so renaming a substitution, there I used functor and monad instances, which I think is a very bad idea. I think people these days start to become aware that you should use normalization by evaluation instead. And then here, these 5 components I've been able to put under a common abstraction, which caused some improvement, but still this was a disaster to maintain, let alone develop further. And the ideal scenario is actually this, where you consider the language as just some algebra. Each syntax operation is just an algebraic operation. Each program component is just a model or an algebra of this thing, and then all you need is a fold, basically. And these 2 papers actually, well, I'll mention them in a minute. These 2 papers actually achieve that. So Allais, Atke, Chapman, McBride, and McKenna start from a universe of syntaxes, which Fiore and Szamozvancev have identified to be the collection of what I call equation-free second-order multisorted algebraic theories. More on them later. AACMM start from a certain semantics, which Fiore and Szamozvancev generalize to just models in the algebraic sense. Both have fully formalized their approach in Agda. AACMM implement many applications, and Fiore and Szamozvancev have a strictly more general approach, which is also mathematically maybe more elegant and profound. But together with these applications, the combination is pretty cool. And so to show you some of the power of what AACMM do, so they have this universe of syntaxes, which contains a bunch of lambda calculi, untyped one, simply typed one with bidirectional annotations. A bunch of common extensions are possible, and more generally, it's all second-order maths. And the results they achieve are, well, renaming a substitution once and for all, pretty printing maximally generically, scope checking once and for all, bidirectional type checking for the lambda calculus, so that's a specific language, but with clear potential for generalization, dissugaring let once and for all, irrespective of the language, and somewhat generic, unsafe normalization by evaluation. So the central thing is that they program generically against the second-order maths. So let's see what algebraic theories are in the first place, and I'll start with equation-free algebraic theories. An example of that is pointed magmas, which are basically monoids without laws. So an equation-free algebraic theory is basically just a container. You have a set of operations, each with an arity. So here we have a nullary neutral element and a binary multiplication. Then from a container, you get a container functor. So the elements are either the neutral element with 0 subterms or multiplication of 2 things in X. Then we can take the free monad over this, which is essentially the term monad. So its elements are either a neutral element or a multiplication whose subterms are again in the monad, or a variable from the set X that you apply the monad to. And then the models of this theory are the F algebras or F star monad algebras, which here really boils down to pointed magmas. And then if we have this equation-free part, we can put an equational theory on it, which consists of a bunch of pairs of open terms. For example, I can say I want E star X to be equal to X. And so I can impose a bunch of equations, then I can quotient out my free term monad by the equational theory, And then a new model of this algebraic theory is an M-monad algebra, which here boils down to a monoid. I want types, so I want to make this multi-sorted. And so the first thing is I'm going to fix a set of sorts. And as an example, let's look at typed Boolean arithmetic, where I take a sorts bool and a base sort. And now I use an indexed container. So sorts are indexed by operations are indexed by their output sort, and arities are now a list of the input sorts. So here I have true and false, which are Booleans with 0 arguments, and then if has any sort, and its arguments are a Boolean and then an else clause. And then we can again look at the container functor, which now acts on sorted sets, so sort indexed sets. And what you see here is true and false are always in fx bool, and then to get an if expression of sort s, you need an element in x bool, and then 2 clauses in xs. And if I go to the free monad, what changes is that my subterms are again in the free monad, and that I also have variables. And then again, the models are still just the algebras, but now they are also sort indexed. Now let's move to the second order part. What changes here is, first of all, I'm going to define contexts and telescopes as lists of sorts, and then a judgment is a pair of a context and a sort. I'm going to use a turnstile to denote contexts. And then the arity now specifies for every argument not just its sort, but also a telescope of variables bound in it. And let's look at the SDLC. So as sorts, I take a base sort and function sorts. I have a lambda, which creates functions, application which can have any sort, and then lambda, of course, binds its argument in something of its output type. My syntax functor now acts on judgment indexed sets. And so to create a term, I could say, in this judgment, gamma of type sort, I need to give an operation of output sort s, and then a dependent list over the arity of x's. And when I specify for an argument telescope theta and sort t, I will extend the context with theta and type check in sort t. So what we have here, if I have lambda body of type s to t, I check the body in type t with s put in the context, and for application I do not extend the context. Oh, sorry, I didn't actually mention this part, I think. Oh, wait, I did. Well, yeah, here I said in the body I'm going to bind s, of course. So in the application I bind nothing, and the types are as they should be. And then I can again take the term monad. What changes here is that my subterms are again terms instead of x's. And I also get meta variables. Note that these are meta variables. X has its own judgment, so its own context of internal variables. And so if I want models, I have to throw in the internal variables manually. SOMATs are unfortunately not good enough for my goals, because I wanted to implement multimodal type theory. Where these SOMATs are simply typed, multimodal type theory is dependently typed. Other people are working on that, not me for now. Also, SOMATs are not non-modal, whereas multimodal type theory has modalities mu, which semantically are dependent adjunctions. So in SOMATs, contexts are just lists of sorts, but here I want to be able to extend the context with a lock, which semantically means I'm applying this left adjoint. This is necessary for the introduction rule for the modal types, which acts by transposition of the adjunction. Substitutions here are just lists of terms, whereas here, this lock operation is bifactorial. So if I have a substitution between locks and a morphism between modalities, I can combine them. So this is not possible if you have just lists of terms. However, both systems have admissible substitution, and the reason is that their context extensions are still factorial. So if I substitute a lambda expression, I can substitute a body, and the substitution I use here is applied by f-mapping the telescope extension to the substitution. And here, this lock thing is also bifactorial, so I can extend my substitution and I can push it down the syntax. So the substitution is admissible. This also works for other systems, for example, in dual context systems like the one by Fenning and Davies. I have these dual contexts, so dual substitutions, and then the box introduction rule removes part of the context, but that is also factorial, so I can push up substitutions. There's the amazing right adjoint, which is a type former that's right adjoint to exponentiation. This is not the rule that these people have, but it's the rule that I would like to have, where you can say, in order to create a term of this type, I need to create a term in the exponentiated context. This is pretty weird, unheard of. But it should work because like exponentiating is functorial, so you can push up your substitution, so there shouldn't be an issue. And so the gist of the talk is that what you need is that all context extensions are functorial. And so I'll call that adjunctor because it generalizes a binder, and Latin for binder is junctor, and it sounds a lot like functor. And so that allows me to make one more generalization, so these are the SOMATs, and then I'll go to contextual mats, where I don't say context and telescopes are lists of sorts, I just say context and junctors can be anything. A judgment is still a context and a sort. And then instead of specifying a telescope, I'll specify a junctor, and then for the amaze rule, I can say, well, I'll check so the amaze thing creates something in the amazing right adjoint, and to type check the subterm, I'll type check at sort S, and I'll exponentiate the context, and then you get the rule that you want where you actually exponentiate the context. So what's the status of this? I'm formalizing this in Agda cubical. So I've formalized mats and their models. I'm working on CMATs. The equation-free part has been done. I'm currently adapting Fiore and Szamozvancev's substitution theorem to this setting. And then I want to characterize what are models of CMATs. And then hopefully, because this generalizes ACMM's work, I hope to generalize their results and also to subsume the second order mats. And then show that multimodal simple type theory is a CMAT. Hopefully implement safe normalization by evaluation. And then if you have all of that, then basically you've got all the parts that you need to have a programming assistant. It's simply type, so not proof, but programming assistant. So I hope that it's possible to implement a programming language in cubical Agda. And as a side effect of all of this, I'm contributing to the cubical Agda library. So that's what I wanted to tell you. So thank you for your attention, and I'm happy to take questions.